Okay, fantastic. So let's get into things. We've been talking about a number of different things, all in the category of crystalline imperfections. So you remember we started off looking at ordered solids with this idea of the unit cell. You know, often a cubic unit cell. It's perfect. It's got atoms just the spots that you expect them to be, and it repeats, a massive number of times. But that's not actually entirely correct. I mean, this is something that people struggle with a bit. Is the unit cell then, as I presented it, useless? No. The vast majority of the atoms in a crystalline solid, you pick a piece of aluminum like this, like this aluminum is FCC, and so the vast majority of the atoms in here are in the face center cubic positions, just like we'd expect them to be. And if I took a little piece of this and cut it out and measured the density, for example, it would be almost exactly the theoretical density. So our unit cell is still a really, really good representation of the bulk material, but there's these other important little defects in there. And even in tiny, tiny quantities, these defects can have huge impacts on the properties. So at the very end of last class, I had categorized this. You'll have this in your notes, zero-dimensional, or so-called point defects. See, it's weird today. I don't know, the audio, it sounds to me like it's really echoey up here. Is anyone else finding it too loud? It's about the same as always? Okay. It was just me. Okay. Well, if nobody's really complaining, I'll keep going. It's just me. So we've got these zero-dimensional imperfections or point defects. We're going to elaborate on those in a bit more detail today. What we actually started with in detail was the one-dimensional imperfection or the dislocation. And so, as is the case with many things in this course, I present them in a very specific order, but it might not seem like the logical order. In fact, for this course, I think we've talked about it, a logical way, see, that's we're getting some feedback now. A traditional way to go through the course would be to start with the atom and sort of work up from there, but that's not how I chose to design the course. I want to start with something that you already know, mechanical behavior, and then add on to it, right, with new stuff. So, crystalline imperfections, I actually started with the linear imperfection. And you may think, well, why didn't I start with zero-dimensional? I started with the linear imperfection because that was, as you recall, that was the basis or the mechanism responsible for plastic deformation. So we've already talked, actually, fairly substantially about plastic deformation, in terms of stress-strain curve and atom positions and stuff. So I felt that was a nice way to introduce the topic of crystalline imperfections. So we now see we've got the dislocation that's responsible for plastic deformation. And then what we're going to do is we're going to look at examples of each of these other types of imperfections, 0, 1, 2, and 3, and show how they interact with the dislocation to allow us to strengthen a material. Later in the course, we'll cycle back and we'll look at, for example, point defects in semiconductor devices and how that impacts electrical properties, optical properties as well. But right now, because we're feeling pretty confident about mechanical behavior, we're going to use that as the basis for our discussion. So two-dimensional, these are interfaces, okay, right? We'll look at some of those. And anything really that occupies a volume would be a three-dimensional imperfection. So as a quick review, we had started to get into point defects, as they're often called, last class. And specifically, under the category of point defects, we looked at imperfections. Impurities. That's what I meant. So is anyone having trouble? I just heard some people asking about the words up there. Is my writing too messy, or is it okay? interfaces. So impurities, and I'm going to have to clarify, I mentioned it, just want to make sure it's abundantly clear. These impurities are added to form solid solutions. So that's an important distinction there, right? Because we can add impurities. You could add, if a little bit of sand got into a metal casting, you'd have this little ceramic silica sand inclusion in your metal part, and that wouldn't be good. But that would not be a point defect, because that piece of sand is macroscopic. It's a massive number, 10 to the 10, 10 to the 20 atoms making up that particle. It's not a single point in the lattice. So point defects are individual little atoms that are missing. I sometimes like to just clarify the concept by thinking back to high school and liquid solutions, because the concepts are really the same. So, in aqueous chemistry, you add a solute to the solvent. Say a classic example that you're all familiar with would be just adding sugar to water. Okay, so you add 1 tablespoon of sugar to a glass of water, say at room temperature, you stir it around. You probably know from experience, maybe drinking coffee or tea or something like that, cheers, good. Is that tea, coffee? Hot chocolate, okay, well that's a complicated solution there, yeah. Yeah, sure, why not? We clap, so let's go. I love the energy in this class. Never in my career have I clapped for a student drinking hot chocolate, but hey, why not? That's great. I love it, yeah. Hot chocolate. What's your name? Farron? Farron's drinking hot chocolate. All right, good. So it's Friday, right? Okay, so, but in that delicious hot chocolate, there's sugar, okay? And the sugar is dissolved. It's dissolved, and so that means it actually exists as, we would call them point defects, really. There's molecules in that case, which is a little bit of a distinction from atoms. But they're moving around in solution, and if you put a lid on that hot chocolate and you left it there for 1,000 years, as long as it was sealed up and the composition wasn't changing, the sugar would never precipitate out a solution, right? Because it's a solution. It's truly a solution. If you took some sand instead of, you go to Tim Hortons, right? You say, oh, can I have a double-double? And they say, well, sorry, we're out of sugar, but we got this really nice sand. And so they add sand in. They put a teaspoon of sand, they stir it around. You're going to know right away. You stir the sand, no matter how much you stir the sand, it's not going to dissolve. Later in the course, we'll see that actually it has some finite solubility, but it's negligible, right? And the sand precipitates at the bottom. I mean, it stays actually as a solid state at the bottom. So silica added to your coffee is a second phase. It's a three-dimensional imperfection. It's a volume defect. But the sugar, when it dissolves, forms a solution, okay? And it's a big stretch often for students to think about this in the solid state. Because really, for this course, we're going to live in the solid state, right? And a metal, like this aluminum right here, is mostly FCC aluminum atoms. But there are copper atoms in there as well to make this alloy. And the copper atoms, some of them exist as just isolated copper atoms in they're probably substituting in the lattice. But they're in solution. Some of the copper has also formed compounds, ceramics. And when the copper forms a compound, that actually becomes a three-dimensional imperfection. Another example, carbon added to iron to make the frames of the tables that you're sitting at. The carbon, we talked about last class, forms a solid solution, right? It goes into these interstitial sites because carbon's a lot smaller than iron. But as we'll learn later in the course, once we cover some thermodynamics and get into phase equilibria, some of the carbon also reacts to form iron carbide, Fe3C. And that iron carbide is now a new phase. And so it's got a different crystal structure. BCC iron is one structure, and the iron carbide is different. So this iron carbide is a three-dimensional imperfection, while the isolated carbon atoms in solution are point defects. So there's a lot of stuff to process there, and I find students quite often struggle with the distinction between point defects and volume defects, and that's okay. You give it some time, and we'll make sure we get all that sorted out. Okay, so we're talking right now about adding impurities to form solid solution, and here's some new stuff now. What we covered last class was just looking at a edge dislocation interacting with a carbon atom in an interstitial site. So here's our old favorite edge dislocation, okay? And you remember one of the characteristics of a dislocation is that there's some strain in the lattice, okay? There's some compression above the dislocation line, and there's some, let's see if there's some tension down here. So there's all this strain, and some students asked me really good questions after last class about what is that strain. I mean, the strain, and you think back to the interatomic force separation curve, is really, it's elastic strain. It's atoms disturbed from their equilibrium interatomic spacing. So there's elastic stored strain energy in this lattice. The presence of that defect elevates the energy of the system a little bit. So, in fact, in that demo last class with the, I think I still have them in here, right? This brass bar, this brass bar now that it's bent actually has more energy in it. It's at a higher energy than it was before I passed it to the students to bend. So there's a little bit more energy in there. And interestingly enough, if I put this in the furnace then, or actually what I did before I brought it to class is I straightened it out in a vise, and then I took a torch to it. I took a blowtorch to it, and I held the torch on it for about 5 minutes to relieve some of that strain energy, to soften it up again so I could do the demo again. And those are things we can get to a little bit later in the course. But what I want to think about now is, let's just say we have this imperfection here, this point defect. And I'm actually going to make the crystal a bit bigger here, sort of cartoon depiction. So that way over here, I can add a point defect. So we've got now, or very shortly, we're going to have two imperfections. So far we've got one imperfection, a linear imperfection on the left. And then I'm going to go ahead and I'm going to add in, say just for simplicity here, I'm going to add in interstitial impurity. And we'll make it, what color? I'll make it blue, okay? So there's an interstitial impurity. Oh, just a little bit of terminology. When we add another element to a metal, what do we call that? Does anyone know? An alloy. Okay, a lot of people have heard that. Fantastic. So that makes it an alloy. That's a term that's often used. So this is, now become an alloy with that impurity there. And what we said last class was the presence of that interstitial atom is just taking up a bit of space. Okay? It's like you're sitting on the aircraft, ready to go home for your holidays or something like that, and you get on the plane early and you settle in, and you've got an aisle seat maybe. There's someone with the window, and there's that one extra seat in the middle, and you're like, it's empty. You think, oh, it's great, it's going to be a good flight. And then you see someone walk down the aisle, right? And you're like, oh, please don't be sitting in this seat. Maybe they're really, pretty big person. And then they sit down. What do? Well, nothing you can do because it's their seat, right? But you go like this. You can't use the armrest anymore, right? You can't, that big person comes down and sits there. You've got to just make a bit of space. I don't know. Some of them have these analogies in my head, and I don't know if I've thought them through, but does anyone know what I'm talking about? You sit, even on the subway, right? Someone sits down, and you're like, yeah, you make a bit of space. So that's what's happening over here. There's a bit of space here being taken up by the carbon, that interstitial atom, and so it creates some strain in the lattice. So here's what I want you to think about conceptually. If you look at that sketch, as I've drawn it there, we've got elevated energy in the system from the linear imperfection, the dislocation. We've got elevated energy stored as lattice strain, elastic strain, around the interstitial impurity. If you were sort of conceptually trying to put into the lattice an impurity atom, when you already knew there was a dislocation, is there another way you could set this up that would have overall lower energy? Is there another way that we could do this to decrease the energy of the system? Actually, why don't we make this a little activity? I'm trying to use this room, right? Let's give you a couple of minutes at your tables, talk with your neighbors about another arrangement that would actually have a lower energy overall. Okay? So go ahead, discuss at your tables. So this wasn't the one I was thinking of, but it seemed right. So why don't we try it out? So I think he showed you, right? When they press the button at the table, it'll pop up here in the queue. And then you can press it and turn it on. Like, so someone over there has pressed, oh. There's always that one troublesome kid. Yeah, so then you got to touch here. Oh, I think, yeah. Right. So if you go here, add to queue or microphone on. Yes, and then you can see his mic's on. Yeah. And then you can kick him off, I think. Probably do that, yeah. Perfect. Thanks. Yeah. The whole room, yeah. And then the tables are numbered as well, so you can try it. Okay, so it's probably been a couple of minutes. Let's bring it in. So, are there any tables that think they have a good answer that they could volunteer? Sure. We'll try to use the mic. So press the button on your table, and then we'll activate your mic. All right. So go ahead. Is it? Oh, yeah. Yeah. So we should be able to just go here, and then mic on. Yeah. Okay. I think we're in business. So you said that the interstitial atom could go underneath the dislocation. Yeah. Okay. And okay, so good. Let's see. Is there someone else in the queue? So why don't we take the next one? Thanks for your pay. Okay, so let's see. Back up there. Okay, yeah. So towards the back there, yeah. H11. E, F, G, H. Where's H? Very back?
We actually had the same answer.
Oh, yeah, okay, you had the same answer. So could we take it a step further? Could you explain why, though? Why did you say that we could put the interstitial atom in the dislocation line?
We believe that the most space is there. So that would be the...
Yeah.
That would be the place for...
Yeah. Okay, so that's a good description, yeah. So why don't we clean this, and then I'll move on, and we'll do the other activity later. Yeah, pretty clear all. Okay, good. So thanks for bearing with me with that. Thanks, Will. Yeah, so absolutely, and I imagine probably a lot of people got that intuitively. You realize that if you could put the interstitial atom over here, there's physically more space in the lattice in the dislocation line. There's an unsatisfied bond above. There's just actually physically a little bit more space. The lattice is strained there. And that's absolutely true. There is more space there. And if the impurity atom existed there, it would create a lower energy for the system overall. And that's a good sort of message to keep in mind in science in general. Things tend towards lower energy, right? I probably shouldn't say it. Okay, well, I'm going to say it anyway because it's Friday. This will be for half the class. The men's washroom, the urinals, right? You know, if a couple of them are being used, where are you going to go? You could go and go right between the two people who are using one. But that creates a little bit more energy, right? Because people are like, hey, what are you doing? Lower energy position is to just take one that's a little further away. Anyway, so the same thing's happening here, right? Where could this carbon atom or this interstitial atom exist? Okay. So I'm gonna bring, you've been really, really good with the conversations, and I know it was a little inappropriate. I apologize. So how does that happen? Well, you can probably appreciate you don't have the ability to just position an individual carbon atom. I mean, we can do that in certain cases, but not in a massive quantity. But how could you do that? Well, what happens is, with time, if you leave it for sufficient time, impurities tend to diffuse, impurity atoms diffuse towards the dislocation line. And then what happens is, that acts to pin the dislocation. It sort of locks it in place. Because from an energy perspective, you can appreciate now for the dislocation to break free of that impurity atom takes a little bit more energy than if the dislocation and the impurity existed separately. And it's a fairly simple sort of concept. And right, in first year, you get it. But this is really relevant, actually, in a lot of processing. Especially a lot of steel alloys have a significant problem during deformation. This is a little aside. You don't actually need to know this. But the stress-strain behavior for many steel alloys, or some steel alloys, looks like this. It's called the yield point phenomenon. If you look in the textbook, you might see it. And what happens is, you get this initial linear elastic region like we've seen, but the carbon atoms are locking the dislocations in place, they're pinning them. And so you've got to it's almost like a static friction kind of thing, where you've got to get beyond a certain threshold to break the dislocations away from the impurities. But then once you do that, it drops back down to a lower stress, and the dislocations can move. And one problem with that, though, is if you deform a piece of steel into sheet product, say you're going to make a car, side panels of a car, when you have that type of behavior, it creates these unsightly lines on the surface. They're kind of micron scale, but it's enough that you can actually see them with the naked eye. And nobody wants a car with these little sort of streaky lines on them. So we need to think of a way to deal with that. And what we do in practice in manufacturing is it's called an annealing pass. We do a little deformation just to move the dislocations away from the impurities, and then we can do the final deformation with the dislocations already sort of freed up. But if you leave it for enough time, like if you close your facility down for the holidays, and the steel's sitting there in the yard, even a couple of weeks is enough time for the carbon to diffuse back to the dislocations, and you got to start again. Anyway, digressing ever so slightly. So anyway, that's kind of another more detailed look at using point defects as a way of strengthening metals. Further thing I should just mention is we also have, under the topic of point defects, you can also have substitutional. Impurities. So substitutional impurities occur when you've got two, or they can occur when you've got two elements that are similar atomic size. The rule of thumb is about 10% in an atomic diameter or radius. Same crystal structure, right? So two things like copper and zinc, both FCC, or copper and nickel, both FCC, right side by side on the periodic table. So almost the same atomic diameter. They form, actually, copper and nickel form a solid solution across the whole range. You can go from 100% copper and make alloys all the way over to 100% nickel, and it's always FCC. There's never a second phase. It's really neat. Same crystal structure. And then something we haven't really talked about, but I think you're probably familiar with, similar electronegativity. Because if they have a really big difference in electronegativity, they're more likely to form a compound, which, as we said earlier, would then form a three-dimensional imperfection, not a point defect. Quick schematic for a substitutional impurity would just be, your lattice, whatever it is, and I'm just drawing a simple square lattice here. And then you've got your second, your solute occupying one of the normal lattice sites. So it's substituting for the solvent atom, right? Substituting for the solvent atom. And that can happen. Okay. So another point defect that we should talk about is the vacancy. Okay, good. And I want to show you that here with this little demo I've got over here. Let's see if this works. Okay. So I've got this little demo. It shows up much better actually on an overhead projector where you can just see the shadows. But it's basically there's a couple of sheets of plexiglass with a whole bunch of these little BBs in between them. And they kind of illustrate, it's a simple, two-dimensional mechanical model of atoms in what's going to be an ordered solid. So if I kind of have them moving around like this, and there's a lot of motion, a lot of room between the atoms, that's simulating atoms in the liquid state, okay? If I then kind of tip it a little bit, you'll start to see that some order has developed, especially if you look over here, right? You can see, say in here, right? This highly ordered arrangement of atoms. I mean, in fact, do you notice anything special about the arrangement of atoms here? Yeah, it's close packed, isn't it? It's a close packed plane. Why is it close packed? It's close packed because that's a low energy configuration for these balls in 2 dimensions. But it also, in 3 dimensions, when you form an ordered solid, it maximizes the number of nearest neighbor atoms. And that reduces the energy of the system. And we'll cover this in a little bit more detail later in the course. But that's the same kind of arrangement we see in 3 dimensions. This is just a 2-dimensional slice through it. So there's all this order. And unfortunately, there's all this glare. But oh, that helps a bit. Okay, so what else you can see, though, is there's some places where, let's see if I can bring it over there. There's a missing atom. Okay, and let me see if I can bring this. So can you, I don't know if you can see, right in there. See, there's a little missing atom. And in fact, there's something else. There's a place where the atoms are arranged over here in one orientation, but then the order over here sort of seems to start at a different orientation. And right along through here, can you see that? It's kind of like a boundary. It's disordered. They don't match up. That would be a grain boundary, which we've actually saw before. I showed you the zinc atoms, you know, and the brass atoms. I showed those pictures of the binoculars at Center Island and the zinc on the galvanized steel. So we saw all those grain boundaries. We're seeing it here, where the 2 crystals are not matching up. Now, if I continue to tip this, and I kind of want to simulate heating, so if I took a piece, like I took that brass from last class, and I took a blowtorch to it, what's going to happen? Well, I elevate the energy of the system, so I increase the atomic mobility, and the atoms can they can move to lower energy sites. So what happens? Well, dislocation density decreases. You get dislocations that sort of cancel each other out, like a positive dislocation, as we've been drawing here, and a negative dislocation, where it's like 180 degrees. They come together, they cancel out, it reduces the energy. Grain boundaries, like you can see here. I don't know if you can see it too well in here. This really shows up better. Let me see if I can try this light. Is that better or worse? That's probably, I don't know. Is that worse or better? Or about the same?
Stronger glare.
It's more glare, yeah. It's just, do you want the glare there? Or do you want the glare here? You want the glare there? Okay, so, sorry, let's, so, it doesn't show up too well, but if I, you can see it there a bit, maybe. Can you see there's kind of these regions where there's all the atoms are arranged in one particular arrangement, and then over here, they're arranged in another way. Over here's another. So these are crystals, they're grains, you can see them, right? And if I take this and I want to simulate heating, what I can do is I can just sort of tap it a bit. And what you should see, if it works, is you should see grain growth. Can you see that? Right now, there's all the way through here, there's one big grain, there's another grain over here, and there's kind of a grain on that side. There's really 3 main grains. If I continue to do this, what happens is the small grains get consumed by the bigger ones. That's what happens. And so if you look at this now, you can see that there's really 3 main grains, one big grain in the middle. In fact, look at that. Can you see that guy right there? Look at him. What's that? There's a vacancy, isn't it? Yeah, isn't that beautiful? What's wrong with this? Why is there a missing atom? There's a vacancy, right? Can you see that? Okay. You're wondering, how long am I going to show a vacancy, right? Okay, so let's move on. But that's beautiful. Look at that. Okay, so there's your vacancy. We'll leave that up. Okay, so these vacancies are always present. You can't get rid of them. They're always going to be there. There's a thermodynamic basis for it. But they're... You could say they're thermally generated. And so if you go to higher temperature, you get more of them. Lower temperature, you get less. And one way to think of these is, you know, the atoms in a solid, they're sitting there in their lattice. And, you know, that's not captured in this model, the fact that they're actually moving around. right? There's above absolute zero, the atoms are oscillating around. Something like, I don't know, 10 to the 12 times per second or something. They're sort of vibrating around. And every time, the atoms are, if you don't mind that I sort of anthropomorphize an atom, the atom wants to break free. It's jostling around like this, and every second it's making, a massive number, millions, billions of attempts to get out of its lattice site. But most of the time, it's unsuccessful. Every once in a while, though, one of the atoms makes a successful jump. And so the atom that used to be there moved somewhere else in the lattice, maybe to a grain boundary, to a dislocation line, somewhere else, right? The atom doesn't disappear from existence. The global mass balance is maintained. It still exists, but it's just not there. And that's what the vacancy is. So it's this competition between that thermal energy and the binding energy that's holding it in place. And when you have that competition like that, there's a common way that we represent it. And I'm going to give you this equation for the number of vacancies relative to the total number of atom sites. So this is number of vacancies versus total number of atom sites. Sometimes people struggle a little bit with what I mean by that. If I wanted to describe this class, I could say two things. I could say absolute number of empty seats. So there's 100 empty seats maybe scattered through this lecture hall. But that's not really useful to you unless you know how big the lecture hall is, right? But if I tell you this lecture hall is 80% full, oh, now that's meaningful, right? Now you get a sense for how full it is. So you could present this equation as the absolute number of vacancies in a sample of a certain size. All you need to do is move the denominator over to what I'm going to show you on the right-hand side. But I prefer to show it as a fraction, just because I think it's kind of a little bit more intuitively meaningful. But when you've got this competition, like I said, between sort of the binding energy and the thermal energy, and it's thermally activated, we express it as this form. Your textbook uses this letter, Q sub V. And I'm going to define that first. Q sub V is the energy to form a vacancy. Or conceptually, that's the negative sign of on the binding energy, right? The energy holding it in the lattice is the negative of the energy required to move it away from the lattice. And it's competing with the thermal energy. So how do you express the thermal energy? And that's something we'll get to a little later in the course, but we express it, and anytime you see this product of the Boltzmann constant and the absolute temperature, that's capturing the thermal energy. So this is this competition between binding energy and thermal energy. And down there, T, that's the absolute temperature. So that's in Kelvin. And this is the Boltzmann constant. Okay, so that's a relatively important equation. I like to describe it intuitively so you kind of have a sense for it. So this tells us if we increase the temperature, we'll create more vacancies, and if we decrease the temperature, we'll have fewer. But something that students sometimes get a little bit hung up on, and I remember myself, I was kind of confused by this. I thought, well, if that's true, if vacancies are formed when an atom makes a successful jump out of its lattice site, why doesn't it all just melt, right? Like if one atom can successfully break the bonds to its nearest neighbor, doesn't that mean it's ready to melt? And the problem with that is that, and the reason that's not the case, is that there's actually a distribution of energy levels in the atoms. So at a particular point in time, one atom might actually have an elevated energy and make a successful jump and create a vacancy. But most of the other atoms don't have enough energy to do that. So there's a distribution of energy levels. All the atoms in the population don't have this exact same energy level. And one way that that's characterized is with this so-called Boltzmann distribution. And I just want to show you this now. We'll cycle back to it a little bit later in the course when we talk about thermodynamics. But I want to introduce it now so you can start to think about it. Because if you understand this, I think it'll really help you to get a deeper conceptual understanding of the concept of entropy. You might have a sense for entropy disorder, but that's a superficial description. There's a better description. We're going to get to it later. And if you see this now, I think it'll help you to understand that. So what we can do is we can plot the number of atoms across the available energy states. And I guess what I'll do today is I'll just do this. I'll say, well, if the system is really cold, at a really low temperature, the distribution would kind of look like this, where most of the atoms, or most of the particles, I'll just call them atoms for now, occupy the low energy states. On the other hand, at a high temperature, you'd have a distribution that starts to look more like this. Right, and it's an important distinction. You know, it's not shifted towards only the high energy states being populated. High temperature corresponds to a distribution of the particles across all the energy states. In fact, at an infinite temperature, it would just be a horizontal line. All the states would be occupied evenly. So high temperature is atoms broadly distributed. Anyway, when you look at this, it gives a little bit more meaning, I hope, to this equation for the generation of vacancies, because you can see, okay, there's a distribution of energy states. Some atoms will be able to make a successful jump and create a vacancy, but maybe most of the other atoms will not. Okay? Got 2 minutes left. So, in the 1 minute we have remaining, I'll show you probably the most important two-dimensional imperfection. And we've already seen it. It's the grain boundary. And why is that an imperfection? Well, you can see even from this model with the BBs there, atoms are going to be arranged, in some kind of a lattice. So if you permit me to not draw the atoms, I'll just kind of draw the lattice. That is the orientation of the atoms. This one here formed randomly at another orientation, and they don't match up exactly at the boundaries. They might be close to the right angle, but they don't match up exactly. There's some mismatch at the boundary. And we can explore that in a little bit more detail later. I know I'm out of time. So with that, have a fantastic weekend. Get lots of sleep, eat a healthy diet. Thanks so much.